Hello and welcome to Chapter 7. So in Chapter 7 today we are going to cover dynamic routing. So we'll talk a little bit about dynamic routing and we will configure RIP2 using the IPv4, and we're also going to do RIP next generation. So I'll show you how to do that as well. We'll talk about the link state dynamic routing protocol and how it works, and take a look at the routing table as well. This is a little bit of a long chapter, so hopefully you can hang in there. The packet tracer that we build, I want you to make sure that you build it and then submit that as homework, in addition to all the questions that I will ask. Okay? All right, dynamic routing protocols means you are going to run software on the routers, and these softwares on the routers communicate with each other. The routers communicate with each other, and they build their own routing protocol. This has been happening since the late 1980s. And now you have IPv6 involved. So all the old RIP version 2, EIGRP, OSPF, the IS, and the BGP protocols have all been upgraded to support IPv6. Okay, routing protocols are used to facilitate the exchange of routing information between routers. So they are the one that they pass updates to each other. So, for example, if I'm a router and I have network A and B attached to me, so what I do is send that automatically that information to my neighboring router, telling them, hey, network A and B, I have network A and B. If anybody wants to reach me, just send them to me. So, and then that router, my neighboring router, pass that information to their neighboring routers, and so on. Okay. And eventually, when everybody gets the information, they'll build their own routing table. They pick the best route. No, what does that mean? The best route? It means the quickest in most general. There are different protocols. Some will use the shortest distance. Some will use the fastest way, with the highest speed. Others will use uh, speed on the highway, for example, and if there is any delay, they'll make into that consideration. Well, they'll take that into consideration. We'll talk about that when we get there. But that's what dynamic routing protocol does. So there are three main components. There's the data structures. The routing protocols they use tables, they build tables, and from the tables they pick and they choose the best route to the destination. They send out messages to each other, routing protocol messages to communicate to other routers. And the algorithm, the program that figures out the best route out of these tables. So once I gather all the information, there's an algorithm, a program that picks out the best path and calculates the best route to your destination. Each protocol, RIP2, EIGRP, OSPF, has an algorithm that figures out the best path to the destination using different metrics. We'll talk about that as well when we get to it. So for example, here are the routing protocol in, excuse me. So here, EIGRP, for example, they send messages to each other, and each router will build their own um, tables, and then dual, the diffusing update algorithm. This is the algorithm, the program for EIGRP, looks at the tables and builds the routing table, which means it picks the best route from the destination. Here are the different messages that they communicate with each other with EIGRP. They send hello packets, update packets, query, reply, acknowledgement packets between each other. EIGRP is not covered this semester. I think it's covered in the following, if I'm not mistaken. And we'll get to that anyway. So the advantages, of course, of dynamic routing protocol is that it automatically shares information with all the other routers, and they help the administrator, the routers help the administrator not to get involved with static routing, of course, and they always pick the best route. And if there is any problems with the best route, then the routers will recalculate or reroute themselves to get to the other destination. Now, because of the algorithm and the tables that you have to maintain to figure out the best route, you need a lot of memory and fast CPU. So that's kind of a disadvantage. So you need a good router to run these routing protocols, especially if you're running EIGRP. That does not mean you should not use, by the way, static routing. Static routing is still useful. You need it, for example, when you want, if you have a stub network, you should definitely use a static routing. For example, there's a lot of companies, even campuses like we have on our campus, a router that's directly connected to the ISP. So our network is considered to be a stub network. So therefore, it makes sense to use a static route, a default static route to the ISP. We'll play with that also today. We'll do some of that today as well. Um, it's a small routing table, 1, 2 commands, and you can handle it. All right. So static routing still has useful, and they can work together with routing protocols, dynamic routing protocols. And remember, a lot of times we write static routings, the floating static route, in case the routing protocol, for example, EIGRP, lost its link. We'll have a floating static route that points to um, to a different direction. Remember what a floating static route is? Floating static route is the backup route. That way you have to put the administrative address at the end. Okay, so here's a stub network, and your only destination is this. So you would write only one command that will go to the other end of the router, right? And so is this, unless you have another one that goes out to the internet. But in our examples, by the way, we will use dynamic routing, even though we'll have two routers. So here are the static routing advantages and disadvantages. And I think we covered it. I think it's not last chapter, it's the chapter before, right? It's secured, easy to implement, but it's not suitable for big, huge networks, right? All right, so question number one, I want you to write this table down for static routing, the advantages and disadvantages. Oops. And I want you to write question number two, I guess, the advantages and disadvantages of dynamic routing protocols. And by the way, question number three, in your own words, explain to me the difference between a static and a dynamic routing protocols. Okay, so explain what static routing is and what is dynamic routing is, and give me some examples if you can. All right, so how does dynamic routing protocol operate? In general, the operating is really what you do is, for example, you go to the router and you enable a static routing, a dynamic routing protocol such as RIP2 or EIGRP or OSPF. You activate it, and then you tell the router which networks you wanna advertise to your neighboring router. That's basically it. And you do that on all routers have to use the same routing protocols when they are sharing updates. And once that's done, then all the routers will get all the information, build tables, and then the algorithm in the router will build and pick the best route out of the destination. We'll pick the best route from these tables and insert that route in the routing table. Okay, so here, for example, let's say we cold start the router. Just give me 1 second, guys. Gotta do something really quick and I'll be right back. All right, let's continue. Going back to where we were. Let's assume that we have three routers, as you can see in this configuration. Router 1, router 2, router 3, and on this side we have LAN 10.1.0.0. This link has 10.2.0.0. This link between router 2 and router 3, 10.3.0.0. And the final one, it's 10.4.0.0. And let's assume we're running routing protocols between them. When you turn on the router after post runs and then Bootstrap loads up the operating system and the configuration in there, the router immediately We'll insert, this is the routing tables. We'll say, hey, network 100 is directly connected to my fast Ethernet 00 interface right here. And I also have another network 10200 directly connected. So each router will place in the routing table what's directly connected to them, right? That's the first thing they do. This is, by the way, if you're running RIP2, right, a dynamic routing protocol. So that's the first thing they do, all right? Each one will, by the way, how did you get these directly connected routers? That's because you went to the interfaces, you typed in an IP address, a subnet mask on these interfaces, and you typed no shut, no shutdown. As soon as you type no shutdown, that immediately enables the interface, and then the router goes in and figures out what network is attached to that interface. And that's how you get the directly connected interface in the routing table. Now, the next, what you do, this router goes in and says, I got network 10100 and 10200. So R1 will send that update to router 2. Router 2 will immediately say, hey, 10100 came in from serial 000, and it's one hop away, right? Puts it in his routing table. And he also gets 10400, right, from this guy. And 10400 came in from serial 001, right? And that's one hop away. So that's the first exchange, right? And this guy send him, he has 10 serial. So for example, if anybody sends a packet that is destined to anyone in 10400, it's going to go out of serial 001, right? Now, still, anybody in 10100 will not be able to ping anybody in 10400. Why? Because R1 still doesn't have anything in in his routing table about 10400. In the next update, router 2 is going to send him that information. And then he puts it in his routing table. And remember, it's going to be what? 2 hops away, right? So let's take a look. Here is the next one. R3 gets it. And now the next update. So look at R1 now. R1 now has 10400. It came in through his serial 000, and it's 2 hops away. Who gave it to him? R2. So R2 gets it. Now R1 gets that. Now if anybody wants to ping R4, now will be successful. So when you send R4, it goes to here. It's 2 hops away because it's 1 hop, 2 hops, right? By the way, anytime you send an update, you take these and you increment the hop count and you give it to your adjacent router. So now if anybody wants to ping 10400, you send that to router 2, and router 2 looks up his routing table, says, oh, you go into 104 whatever, you got to send it out of serial 001. And it goes out to reach R3, and somebody in here will be able to reach 10100 because it's also 2 hops away. You see, by router sharing with each other, they'll be able to build their own routing table. Every 30 seconds, RIP2 will send updates to each other. That's called periodic updates. So remember this. How often, question number 3 or 4, I should ask. How often does RIP2 send updates to its neighboring routers? The periodic updates every 30 seconds, even if there is no changes. If there is changes, there immediately will trigger an update. All right, so there is you have the router now has converted. By the way, all of this has, they're explaining to you exactly what's going on, so you can read this in details, but I just went over it with you. So once the routers get all the updates together, they immediately and they build it and they figure out the best route, and I have all the information about any network that I want to reach in my LAN. That means the network has converged. Now, it may take a long time to converge. If you have a lot of routers, you want routers that can converge very, very fast. It is considered that RIP is slow to converge, but EIGRP and OSPF converge much quicker. We want a router that is able to converge very quickly. Imagine this. Here's an analogy. Remember, we always said that the routing protocols are like post offices, right? So do you want to go to a post office that is running RIP2, which means every 30 seconds, the guy in the post office, which is the routing protocol, closes the doors and says, I have to communicate and talk to other post offices next to me to figure out if there are any changes in their networks. Every 30 seconds, he cannot route packets. Or do you want them to be these post offices or these routers running EIGRP or OSPF, which means they leave the door open 24/7. They only communicate in the very beginning with each other, and the network will always be converged. There is no periodic updates with EIGRP or OSPF. So that's much better, right? Now, here how you can classify routing protocols, the dynamic routing protocols specifically. There is the interior gateway routing protocol. This is ones like on campuses, like in Rutgers University, for example, or on our campus. And if they and these are either you can run OSPF or EIGRP, the latest down here. Either we use link state protocols, which we'll talk about in a few minutes later on. What's the difference between link state and distance vector? Now, to route between these interior gateway routing protocols like these campuses, you would go to the border gateway routing protocols, BGPs. We really don't get involved with BGPs a lot because ISPs use them mostly. Those are called exterior gateway routing protocols, which means they route between interior routing protocols. All right, so here's an example. Here's an autonomous system, AS1, right? There's a whole bunch of routers, one big, huge campus running EIGRP on each of these routers. Now, to route between this AS and this AS, you use a BGP between them. So it's a lot more sophisticated routing protocol, the border gateway routing protocol, right? We're only going to be doing the interior in here, interior gateway routing protocol, not the exterior gateway routing protocol. The most famous exterior gateway routing protocol is BGP. All right, now there are two different types of dynamic routing protocols. There are the distance vector protocols and there is the link state. And what's the difference? Well, distance means how far are you? How far does not really, in data communication, does not mean the actual physical distance. It's how many hops. For example, from New Jersey to California, if let's say you have direct connection to California, that's one hop. And if you have, or if, let's say you want to go to Pittsburgh and you go to Harrisburg, then Pittsburgh, Pennsylvania, that's two hops. So which is shorter? It's really California because it's one hop. All right, so the distance means the minimum number of hops to reach a destination. So if you have a destination and you have to go through 3 hops to get there, or 1 hop, you will pick the route with 1 hop because that's called a shorter distance. Okay? Vector means uh, which direction you're going to go, east, west, north, which router. Now, which routing protocols are considered to be distance vector protocols? RIP2 and EIGRP. So question number 5. Which routing protocols are considered to be the distance vector protocols? Well, there they are. RIP1, 2, IGRP, and the enhanced IGRP. Okay, link state, on the other hand, don't care about distance. All they care about, and by the way, just one more thing I want to mention in here. RIP2 has a maximum distance or of 15 hops. So that means if you have more than 15 hops away, you cannot use RIP2. Okay? Anything above 15 hops is called unreachable. So you can't use that. EIGRP has a maximum hop count of 100. You can configure it to be 255, but the maximum is 100. Okay, so remember that. Put that also in the question that I just asked. What's the maximum hop count for RIP2? 15. What's the maximum hop count for EIGRP? 100, although you can configure it to 255. Link state protocols do not use distance. They don't care about the distance. All they care about is the speed of the link. See, link means the interface. The state means the status of that interface. What is the status of that interface? How fast is it sending out data? Okay? So is it 100 megabits, a gigabit? It will always choose the links with the fastest speed, bandwidth, right? So link state protocols, the most common ones are OSPF. This is the most popular because it's not proprietary like EIGRP. It's a proprietary of Cisco. This is an open, that's what the O is for, open short path first. So a lot of people love to use that. Let me give you an example, but the difference between RIP2, EIGRP, and OSPF. RIP2 looks for the shortest distance. Let's say you want to go home and your routing protocol says, "Oh, RIP2, I'm going to get you the quickest way to get home, the shortest distance." You may have to go through, local streets that have lights and the speed limits are very low and there's a lot of traffic, but you pick the shortest distance. OSPF says, I'm not going to go through the shortest distance. I'm going to look for highways, right? So it may be a little bit longer for distance wise to get home, but if you take highways to get home, you'll get there much quicker. EIGRP, on the other hand, says, okay, what I'm going to do is I'm going to look for highways too, but I'm going to make sure that these highways don't have a lot of traffic, no delay. So I'm going to look for highways and plus make sure that there is no traffic too. So EIGRP is a little bit more sophisticated that way. But the problem with EIGRP, well, it's not a problem, is they only run on Cisco routers. They don't run on any other routers. So if you have any other routers, you're most likely you're not gonna be running EIGRP. Well, not most likely, you're not gonna be running EIGRP if you don't have a Cisco router. All right, now do you remember classful routing protocols? Classful routing protocols means that when we do the subnetting, um, every single network will have the same number of hosts. That means every network will have the same slash number. Let's say slash 26. Even the links will have slash 26, for example, right? And we don't like to do that because we waste a lot of IP addresses. But that's what classful means. Every network that's been subnetted, every network in our lands will have the same slash. So therefore, when we send updates to each other, I don't have to send the subnet mask, the slash number, because everybody has the same one, right? So you just send what network you have. You don't have to send what slash it has, right? Now, that's called classful. Only RIP1 and IGRP are classful. But if you do VLSM, VLSM is classless. So because we do VLSM, every single network will have a different slash, right? And if they have a different slash, now when you want to send your updates, you have to send your updates and you have to send the slash because most likely it's different than the one that you're sending. The router that is receiving what network you have, it needs to know what slash also. It needs to figure out what's the network address of that network that you are sending. Okay? So RIP2, EIGRP, and OSPF version 2 and is are all support VLSM. IPv6 then was included later on. Okay? So here is the characteristics of the routing protocols. All right, so again, the most widely used is the link state OSPF, and the reason is because it runs on, it's a link state, it converges very fast, and it operates over not only Cisco routers, non-Cisco routers as well. A metric, for example, shortest distance is a metric to use to calculate. RIP2 uses the shortest distance. That's the metric it uses to calculate the best route to the destination. EIGRP uses the metric bandwidth to calculate the best route to the destination. EIGRP uses multiple metrics. It uses bandwidth, delay, It also has the options to use load and reliability to calculate the best route to the destination, right? All right. So when you send your updates, if you are class full, you send your periodic updates on this network, on this 255, 255, 255, 255 every 30 seconds if you are RIP2. So you send packets on this destination IP address for 255s. And that's really even though you may not have any changes. So that consumes a lot of bandwidth and CPU. That's why a lot of people don't bother using RIP2. So anyway, that's why they prefer to go with they prefer to go with either OSPF or EIGRP when they are running routing protocols. Okay, RIP2 uses the Bellman-Ford algorithm to calculate the best route to the destination. EIGRP uses the dual. That's why you see a little d in the routing protocol, right? The diffusion update algorithm. All right, so for routing information protocol, the updates are on this recipient sent on 520 port. And for RIP2, they send the updates on a multicast address, 224.009. And they support VLSM, they support classless interdomain routing, they support summarization of the route, they support authentication. You see, RIP1 doesn't do any of that and uses a broadcast address to send all the updates. So if you're going to use RIP2, much better. And the maximum hop count is 15, like I told you before. And remember, the distance, administrative distance is 120 in this case. EIGRP sends his updates on 224.0.0.10 multicast address. Pretty much the same as everything else is the same. The maximum distance again is 100. It uses not only delay, bandwidth and delay as the metrics, but it also can use reliability and load as well. And the administrative distance is 90. What does that mean? The administrative distance is 90 and RIP2 has an administrative distance of 120. It means that if you're running both protocols, EIGRP and RIP2 at the same time, the router will use the route that has been found by EIGRP. Why? Because EIGRP has a lower administrative distance. That means the route is more reliable, more trustworthy. All right, so now let's do some router configuration using RIP2. And then we're going to do it in EIGRP. No, we're going to do RIP2 and we're going to do RIP next generation, IPv6. So here we go. So let's go now to Packet Tracer. And I want you to bring in, I'll just blow this up a little bit. Bring in a 228.11 routers. Here's one here, here's one there. Bring in two PCs, a genetic PC right there, and another one right here, PC 0. Okay, open up router 0, turn it off. We're going to put a serial ports in there, put a WIC2T. Of course, you can always pause while we're doing this. Turn it on, slow me down whenever you need to take your time building this up. Okay, close this, open router 1, turn it off, and go place in a WIC2T in there. Turn them back on, right? All right, let's connect them together. And I need the one with the clock right here. That means this one is going to be from serial 000 to serial 000. Let me get a crossover cable from PC 0 to fast Ethernet 00. Get another one from fast Ethernet 00 on router 1 to PC 1. Fast Ethernet 0. There you go. All right, so what I'm going to do is I'm going to say that this network is 192.168.10.0/24, And I'm going to say this network is 172.16.0.0/16. And the link network is going to be 10, 20, 30 slash 30, let's say. That doesn't matter really, to be honest with you. I'll explain to you because we're going to be running RIP2. Okay? Oh, wait a second. Here we got to fix this up because 10, 20, 30 what? Dot zero, let's say, dot zero, right? Okay, let's go to the IP addresses. Give this guy the first IP address. And I go to the desktop and I say you are 10, oh, not 10, 192.168.10.2. What I'm going to do is I'm going to give this dot 2, this is dot 1. That's all. Hit the arrow key because it gets /24 immediately. 192.168.10.1 is the default gateway. Let's go to the other side. Go to the desktop and type in 172.16.0.2/16, 172.16.0.1. Okay, now let's go to the interfaces. Go to router 1 and go to CLI. Type no. We're doing IPv4 configuration of RIP2. Right? We're doing RIP2. That means it's for IPv4. So type en. We're on router 0. So en config t. The host name is R0 and no IP domain lookup. Okay. Let's go to interface fast Ethernet 0/0, which is this interface right here, and give it the IP address 192.168.10.1 with 255, 255, 255.0. That's the subnet mask and no shutting. Okay, let's go to this interface right here, which is the interface serial 000, and give it the IP add 10, 20, 30.1, 255, 255, 255.1. What the hell am I talking about? 252, 252. Now, because it's a DCE, remember when I picked the DCE, I put it here first. So that means I have to put a clock rate of 64,000, and then you type no shut. Okay, I go to the other router. Router 1, I guess, right? Say no. And say en config t host name R1. No IP domain lookup. Go to interface fast Ethernet 0/0, and it's going to be IP add 172.16.0.1. 255, 255.0.0, that's /16, and no shut. And let me go to the serial 000 and say IP add 192.160, what the hell? Come on, guy. 10.20.30.2, 255, 255, 255, 252, and no shut. Now everybody should be green now, right? There you go. Okay, now if I go to router 0, right, and let's just to exit and type exit again and type show IP route. All you see is the two directly connected routers, right? The 192.168.10.0 and the 10.20.30.0 network, right? On the 0.0.0. Now we're going to run RIP2. The first thing you're going to do is you're going to say config T, make sure, and then say router rip. Now, if you leave it like that, you're just activating RIP version 1. It's classless. We can't do that. So you type version 2. You have to spell version correct, of course. Okay, so RIP, router RIP, and then underneath it, you write version 2. Remember that if you've taken your CCNA exam, they may give you an answer, say, oh, activate router RIP 2. And some of the answers may say router RIP space 2. Wrong. It has to be, or router RIP space version 2. That's also wrong. It has to say router RIP, hit enter, then you type the command version 2. Now, you need to advertise networks next. So we want to advertise this network. So you say the word network, 192.168.10.0. So this is what we're advertising. And by the way, because RIP2 has always been classful, it is best to use RIP2 if classful means from the old classes. This is a class C. So as soon as it sees a 192, it will advertise any network that starts with 192.168.10. It doesn't matter what the last number is. So in this case, it sees the 10. So when you type network, you don't have to type 10, 20, 30, 0. You just write network 10, 0, 0. Now, if you wrote 10, 20, 30, 0, it doesn't matter. It will advertise anything after 10 because 10 is a class A. It will advertise anything that starts with 10. That's how RIP2 works, unfortunately. I don't like doing that anyway. Okay? But anyway, so here is the 1000 because it's a class A. 10 is a class A, so you just type in the first number and then whatever is left over. So when we're doing VLSM, you have to be very careful. And when it comes to supernetting, which we'll explain later on, if there is a supernet, you should not use version 2 because it's a mess when you do that. The next thing you should do with RIP2 is you should disable auto summary. So disable auto, no auto S, or no auto S is good for no auto summary. What that means is, remember, by default, RIP2 will always summarize the routes, and that may cause a problem. I'll explain later on, especially if the whole network has not been subnetted. Some networks are not the same as you, and well, anyway, we'll explain that later on. All right, so no auto summary. By the way, EIGRP and EIGRP and RIP2 both automatically summarizes the routes. So we always do no auto summary. And that means it's going to list all the routes, even though they have the same exit interface. Okay? Now, updates are, when you write this command, network 192.168.10.0 or 10.0.0, updates are going to be sent out of this interface and sent out of this interface too, right? So what we want to do is we just want to advertise this network. I don't want any RIP2 updates coming into the LAN because that'll just create a lot of traffic. So how do you do that? By typing passive, type PAS and hit the tab key, passive interface FA0/0. What this does is it will not allow RIP2 updates from coming into the LAN, but it will still advertise LAN 1, advertise it to the neighboring network. By the way, if you did not advertise the link, nothing comes out. If you type passive interface on the serial 000, no updates will leave here. So that means router 1 will never receive any RIP2 updates, and that's not good, right? That's it. So let's go to router 1, repeat the same thing. Go to router 1 and type exit. We're in the config mode. Say router, RIP, enter. We want version 2, enter. And we want to advertise network 172.16.0.0. Excuse me. And then we want to advertise a link to, which is 10, dot 000, enter, right? You still have to advertise. If you don't advertise the link, no updates will go out of the link. Now, updates are coming out of the fast Ethernet too, because the network command, like I said earlier, this network command does two things. Advertises that network plus sends updates through that to that network. So the only way to stop updates from coming into the LAN, but still advertise that LAN, is to say passive, type PAS, hit the tab key, passive interface on the fast Ethernet 0/0. And we also have to do no auto summary. Disable the auto summarization. That's it. You just finished writing to do Control Z and do now show IP route. And there is 0. See, now I learned. So now RIP2 has also sent updates to each other, these two routers. And I see the network 192.168.10.0/24 came in to router 1, right? And it has an administrative distance of 120. It's one hop away. And this is the next hop address, which is this address. Remember, I'm on router 1, right? Excuse me. I've learned it 4 seconds ago. And the updates came in through my serial 000. My serial 000. So there's my entry in the routing table. If you go to router 0 and you do Control Z and you type show IP route, and there's the same thing. Here is router 1 LAN update. Same thing pretty much, right? All right, now PC0 should be able to ping PC1. So let's go to PC0 and ping 172.16.0.2. Excuse me. Okay. And there you go. By the way, the first one always fails because of ARP requests, right? All right. Now that's how you configure RIP2. See how easy it is? Now let's do one more thing. Let's say RIP1, what happens? Let me go back to R1. What happens if a packet comes in and I look at the packet and it doesn't match any of these? What happens to the packet? It gets thrown in the garbage. Remember that? It gets thrown in the trash. Why? Because the gateway of last resort is not set. So we should set a default route somewhere else. So what we're going to do is we are going to create, let's assume that there's an ISP. So if you don't want to communicate with anybody in your LAN and you don't want to send any data to R0, you should go out on the internet someplace to the cloud, right? So for testing purposes, I'm not going to put another router or an ISP. I'm going to create a virtual interface inside the router called a loopback interface and call that the ISP. I don't know if we did that or not, but here's how you do that. A virtual interface for testing purposes. Do go to config T and you type in interface LO, the letter O, for loopback 0. So I just created a virtual interface, software interface that's inside router 1, right? I'm going to give it a description, DES, and hit the tab key and say this is the ISP. Okay, let's just give it an IP address. IP at, I don't know, let's say 50, 60, 70, 80. With 255, 255, 255.0/24. By the way, you don't have to type no shut because the virtual interface will come up immediately. But if you type it, let's say we type it, it doesn't hurt. So now I have an ISP router or interface inside the router for testing purposes. So what I'm going to do is type exit. Now I'm going to do a default route, IP route 0000 space 0000, the quad zeros, to loopback 0. So what this is saying is if any packet does not match any of the entries in the routing table, is going to be sent to the loopback 0, which is the ISP. Let's verify that in the routing table. Do Control Z and type show IP route. And there it is, the static route. So now these people in router 1, if they don't communicate with R0 or anyone in their LAN, immediately their packet will go on to the internet, right? Because they have the gateway of last resort set. Their packets will no longer be dropped if there is no match. But the thing is, on router 0, they don't have that. So if you type show IP route on router 0, they don't have internet. So do you want to connect them to the internet too? We could do the same thing we did on router 1. But here's what we could do. Go back to router 1 and then say, I'm going to tell router 0, if you have any updates, if you have any packet that does not match any of your uh, any entries in the routing table, send that packet to me and I'll send it out to the internet. Which means I'm going to send an advertisement to router 0 and tell them create a default route to me. In fact, if you have a lot of routers running RIP2, router 1 will send that advertisement to all the routers and tell them create a default route to me, right? So here's what we're going to do. We're going to go to router 1, and go to the config mode, go into router RIP version 2, okay, and say DEF, hit the tab key, default information, and then the letter O, hit the tab key. Default information originate, and hit enter. What that command does, it will advertise and tell all the neighboring routers that are running RIP2 to create a default route in the routing table that points to R1, which means if a packet does not match any of the entries in router 0 routing table, the packet will be sent to router 1. So now router 0 should have a default route pointing to router 1 because I just sent that I propagated that default route to them. So go back to router 0 and hit the upper arrow key and hit enter. And there you go. You see R with the star, and now the gateway of last resort is set. That's it. We're done with RIP2 IPv4. Okay, now we're going to do pretty much the same thing with IPv6. This is only IPv6. So let's do RP next generation, RIP next generation, RIP NG, right? So the first thing we're going to do is we are going to assign IP addresses to these guys, IPv6. So let's go to R0. Now we're doing the IPv6 first. All right, so config T to allow us to do RIP to what do you call it? Dual stack. How do you activate IPv6? By typing IPv6 Unicast routing. Enter. Right? Now I go to interface fast Ethernet 0/0 right here. FA 0/0. I give it IPv6 add. Let's say I give it the global address 2001 colon 08 dB colon ACAD calling. Now it comes to subnet. Let's say this is in subnet 1, and this guy is going to be calling 1/64. That's the IP address I'm giving this guy right here. Right? Now I want to change the link to also FE80, the link local to FE80.112, right? So you type IPv6 add FE80 colon 1, right? Type L and hit the tab key, link local. That's it. Now let's go to this interface right here. Go to it. You don't have to type no shut because we're already did it for IPv6 addresses. Say IPv6, let's say it's 2001. We're doing a global IP address, 08 DB colon ACAD. By the way, I'm making these numbers up, so it's not, these are special. I'm just making these up. I'm just making sure it's a global address. ACAD, let's say it's in subnet 2, colon, and he is going to be the first address slash 64. Actually, the slash should be closer to here. Let's see. IPv6 add. I forgot the word add for address. Okay. Let's say IPv6 add FE80 colon 1 link local. Right? Remember, I can give the one. Remember, I type LI and I hit the tab key, right? That's it. How do you verify that these are running? So you do Control Z and type show IPv6 interface brief. Good. 1 1 on the serial ports, and they're both up. Very good. So let's go to router 1 and do the same thing. Do exit. Go to interface fast Ethernet 0/0 and say IPv6 add 2001 colon 08 DB colon ACAD colon. It's in let's create a subnet 3 colon 1 slash 64, right? And do IPv6 add FE80 colon 1 link local. Excellent. Let's go to the serial 000 right here and say IPv6 add 2001 colon 08 DB colon ACAD colon in subnet 2, and he is the other number 2, right? Slash 64 slash 64, right? And we're going to do an IPv6 add FE80 colon 2. He's the other link local number 2, right? Because on the link local, he is already 1, right? Link local. That's it. Do Control Z and then type show IPv6 INT BR for brief. And good. Fast Ethernet, the serial 0 000. Did I do that right? Oh God, I messed up. See? That's why you need to check that out. So this address being given the 3-1 also. Okay, we messed everything up. We got to redo this all over again on router 1 because serial 000 is not being given his IP address. So we have to remove the IP add this one and this one. Okay, the last two from the fast Ethernet 00. So here we go. Config T. You go to interface fast Ethernet 0/0. You know what? Let's do it all over again just to make sure. Say IPv6 add 2001 08 DB colon ACAD colon. This is subnet 2. And he's going to have the first address slash 64. Right? What did we do wrong? IPv6 interface incomplete command. Oh, colon. We got to do 2 colons, right? And then IPv6 add FE80 colon 1 link local. Okay, I'm going to want to make sure show IPv6 interface brief. Now the problem is, you see, the problem is we have to remove this one and this one out of there. 2.2 and 3.1. Because in IPv6 it doesn't overwrite the IP addresses, it just keeps adding them because you can assign more than one IP address to an interface. So here's how you remove them. Let me go to config C, go to interface fast ethernet 0/0, and I'm going to say no IPv6 add. You know what I'm going to do? I'm going to copy no IPv6 add this one, copy it, paste it here, and say //64. All right, and I'm going to repeat the command, and I'm going to get rid of what? The 3-1, right? This is going to be a 1, and this is going to be the 3. Wait a second. These are the 2s. No, 3.1 is good. No. 3.1 is good. 3.1 is good. We don't need to remove this. We need to remove the 2.1 also. The 2.1 should be removed, right? Sorry for screwing this up for you. 2 colon 1. All right, because the subnet 2 is right here. So let me just make sure. Do show IPv6 interface brief. Okay, so I got subnet 3, 1, and he is the first one. Good. Now I go to interface config T. I go to interface serial 000 and say IPv6 add, and he's going to be 2001 colon 08 DB colon ACAD colon. He's in subnet 2 colon 2 colon 2 /64. Right? Because he's in subnet 2. He's in the second one from here. Right? And then he's going to be also the second one with FE80. You don't need /64, and you just say link, local link. And that's good. Now do Control Z, show IPv6 interface brief, and that's better. The subnet 3 is in the here, good. And subnet 2 is here, good. And he got number 2, and he is the link local 2, good. Everything's good. All right, so how do you run RIP and G? It's even easier than RIP1. Do config T and say IPv6 RIP. If you do a question mark, I'm sorry, router question mark, router RIP question mark, router RIP let's see, IP, no. Okay, just give me 1 second. I'll be right back. I have to go do something really quick, and I'll be right back in a few minutes. Okay, we're back. So let's continue. Go back to the router. Now, to do RIP, You actually don't have to do router rip. What you do is you go to the interface that you want to advertise, and you say um, IPv6. If you do a question mark, it tells you can do RIP. You see, you can do OSPF, you can do EIGRP. So IPv6 RIP. Now you give it a name in capital letters. Let's call it RIP dash EXE and the word enable. That's it. So that's going to be enabled. You go to the serial interface right here, INT, serial 000, and you repeat the command. IPv6 RIP RIP-exe. It has to be the same name. Not EXE, just EX. Enable. So now RIP is enabled on both of these interfaces. You go to router 1, you do config T, you go to interface fast Ethernet 0/0, and you say IPv6 RIP, and it's going to be called RIP-EX enable. And IPv6 RIP enable. We've never enabled routing, so do exit. See, there's a good example. You got to do IPv6 Unicast routing. Remember, we never did that here on router 1. So we got to do that first. Then you go to fast Ethernet 0/0, and you say IPv6 RIP. Let's call it RIP-EX enable. Then I go to interface serial 000, and I say IPv6 RIP-EX enable. That's it. So you do Control Z, type show IPv6 routing, and you see this is the network, the subnet 1, right? And it actually shows it's 2 hops, 1 hop here and 1 hop here. Now it's showing 2 hops the next generation. And these are locals, which is the actual interfaces, and the C's means the network. If you go to router 0, do Control Z, and you do show IPv6 route, pretty much the same thing, right? Here's network 3. Okay, if you go to the PC, do the auto config, do the slack, remember that? Bingo, got it. Go to PC1 and do the slack on that guy too, right here. And there you go. Now we should be able to ping this address. Oh, we can't even highlight it. They should be able to ping each other. I mean, if you can type this address, they should be able to ping each other across. But you got to type in this address in here. Yeah, let me see if I can do that on the same page. Oh, we can't do that. Anyway, if you can copy it and ping it, you'll be able to do it. But that's it. All right. So now you know how to do RIP next generation too, right? So let's continue. We were at right here when we're done. If I'm not mistaken, was it? Yes, right over here. Let's go back. Remember that that packet tracer should be saved and sent in as homework, right? So here's how you do IPv4 again. Let's go through the slides. We just did it together, right? You say router rep. This is version 1, right? Because they did not type version 2 underneath. And he advertised 2 networks, 192.168.1 and 192.168.2, right? You could do show IP protocols. It will display all the routing protocols that are running, right? To verify that RIP1 is running. This way it tells you RIP1 is running. So show IP protocol displays all the routing protocols that are running. So question number 6. What is the command that will display which routing protocols are running on your router. And the command is show IP protocols. Okay. Disabling auto summarization, you type no auto summary, right? We did that already. So we don't waste a lot of bandwidth and all of that wonderful stuff, right? Passive interfaces, right? We don't want any updates coming into the LAN, right? For security reasons and for traffic purposes. We did the propagating of the, remember we did a, actually we were on router 0. We did the default route. Instead, we did the loopback 0, right? We did the virtual interface as the ISP. And then we did the default information originate from router rip. This is router rip and router version 2 is the same thing pretty much. Okay, here's how you do version 6. We did that already, right? You go to the interfaces. You don't have to say router rip, but you got to make sure that you're running unicast routing, right? Show IPv6 protocols tells you all the router 6 version 6. See the next generation. If you want to find out if the RIP next generation is running, you type show IP version 6 protocols, and that will show you that, right? Show IPv6 route. Just for RIP, it will just display the RIP, no, nothing else. So that's a good command to take a look at, right? Show the OSPF now, the shortest path first. These, we just did RIP2, which is distance vector. Now, OSPF is the most common link state protocol. ISIS is the one that is mostly used by ISPs. Now, the Dijkstra shortest path, Dijkstra is the one that calculates, that's the algorithm, that's the name of the guy that did that. So what he does is he looks at the cost of each link. Each link is given a number depending on what the bandwidth is. So for example, the shortest path on R2 to reach R3, where's R2? R2 to reach R3 is 20 plus 5 plus 2. So 20 plus 5 is 25 plus 2 is 27. So that's the shortest distance to get to somebody in here from R2. Now, if you want to go this way, it'll be 10, 10, 10, 2. You can come this way, 20, 20, 10, 2. That's not good. So the shortest distance is to go this way. Right? So link state, what they do is they learn everybody using link state packets. They pass that to each other. They build a routing tables, and the difference between link state is they have a map of the whole network, everybody, not just who your neighbor is. It's just like a picture of the whole, every router knows where everybody running OSPF. So you got to send updates to everybody in your router. We'll talk about OSPF in the next chapter in details. Okay. So for example, okay, so that's that. Here is, for example, network 10110. It has, the cost link is 2 and so on. So the first step is you assign a cost depending on the bandwidth of router. Then he goes to each link and does that. Assign a cost. Then you say hello to your routers to tell them, hey, I'm here. I'm R1. I'm your neighbor, right? Your neighbor. And then what you do is you send updates depending on the cost. R1 will say, hey, I got 1010, and if anybody can reach me here, it costs you $2, right? 2. So he sends that LSP, the link state packet, to all the adjacent routers. All right, so he'll send all of that, and everybody will send it to everybody else. And then R1 to R2, R1 to R3, R1 to R4. He sends all of that information with each cost. So this one will cost 20. This one from R1 to R3 is 5. From R1 to R2 will be 20, and so on. And then you build a database. R1 link states, R2 link states, and all the costs of each one of them. So once you build that, then you create a tree, and that's what's called an SPF tree. Okay. For example here, R1 link states. If you want to reach 10.100, it's going to cost you 2. Connect it to R2, 20 is going to cost 20. So you build that. It's like drawing them here, right here, a tree like this. What's connected to you. And then the resulting of the tree, you have the actual topology. So router 1 now have the whole thing looks like, and they can calculate what's the cost to reach every single network. For example, on R1, if you want to reach 10.500, you got to go through the shortest path. The shortest path is to go through R2, and it's going to cost you 22. So you go here 20 plus the 2 to reach the 10.500. If you want to reach 60, go to R3, which is going to cost you 7, and so on. So once you have the tree, then you pick all of these entries goes in the routing table. Okay, so here's your routing table. These are the directly connected. This is the remote ones that you learn by OSPF. Now, link state is very nice because they always pick the best route to the destination, the quickest. The only thing is they do not have backups. Well, they do actually, but they're open and anybody can use them. It's a free protocol. They run on Cisco router, non-Cisco routers. Um, but if there's no changes in the topology, then there's no updates needed. Everybody will have their routing table and the network will always be converged. Unlike RIP2, where you have to send updates every 30 seconds, right? Now, but because of the link state database is so huge, you need a lot of memory and you need CPU, like I said, all routing protocols, dynamic routing protocols, but specifically OSPF. But nowadays, a lot of the routers have a pretty good CPUs in terms of speed and lots of power, so we can run OSPF very easily. Okay. The disadvantages you have to create links. We'll talk about that also. Multiple areas with OSPF. So it's like BGBs running between area 0, area 1, area 51. Each one of those is running their own OSPF, but we'll talk about that some other time. All right, so there are version 2 that runs the CIDR, which is using the VLSM, and there is for IPv6 the version 3 OSPF. So you can type show IP route, and this is for version 4. Right, here's your routing table, right, with all the Rs, all the remote networks, the directly connected routers, right? Now, when you have remote networks, the first one always tells you the route source. This is using RIP. That's what that R is. The metric 120 should correspond with the R RIP, right? This is the destination. This is the subnet mask of the destination. This is 2 hops away, right? This is the next hop address where you're going to have to send the data to. This is how long ago you have learned this entry in a routing table. And this is the outgoing interface. I think I explained this before, right? So routing table terms. We have an ultimate route, which means something like this. Or this is an ultimate route. Level 1 means this one that doesn't have any letters next to it. And anything underneath it is called a child. This is the parent. This has not been subnetted, actually. And all of these are children of this parent 172.16. Right? So the first thing that you're going to do is you go to the router, you go through either the ultimate route or level 1, right? And if you go to a parent, you check the parent. If that succeeds, then you got to go in and check the child. Now, if the parent doesn't work, you can skip if you check the parent and it doesn't match, you skip all of the children and you go to the next level 1, excuse me, ultimate route. But if the parent checks, which is the one that's before subnetting, then you got to check the child routes. If none of them works, then you drop the packet, actually, believe it or not. unless you say IP classless in there, which means it leaves and continues in checking the routes outside. But anyway, this is called the parent, and these are called the child routes. Okay, so an ultimate route is a routing table of entry that contain either the next hop or the exit interface directly connected. Okay, so just like this one, this is direct. This is an ultimate route. Ultimate means you're going to go ultimately to the destination. Even the children is considered to be an ultimate route. Okay, so are these. So a network level one is a network address, and that sends you directly to your ultimate route. A supernet means if you have something like 192, which you know it's classically is supposed to be a slash 24, right? And but you have a slash 16, which means you're using some of the bits of class C address. That's called a supernet. That means you use some of the network addresses as hosts. If you have a slash that is less than 624 and you have a class C address, then you have a supernet. And I highly recommend that you do not use RIP2 when you do that because it confuses you. You can ask me about that in class and we'll talk about that later on. But these are ultimate routes that you can go to. The default route is considered to be a level 1 route 2. So if it matches, it goes directly to the interface. If it matches the supernet, it will go directly to the interface. If it matches a network address and you go directly to the next hop or the exit interface, that means you are also level 1. Okay? Parent route means the one that has not been subnetted route. So it tells you this is a parent, which means 172.16/16 has been subnetted and there are 5 subnets. He's the parent and there are 5 children in there. That's what it's saying. These are the child routes of that parent. So you have to check the parent route and then check the child routes. So here's the lookup process in terms of the routing table. Question number 7. I want you to write the 7 lookup processes and step by step on how the router look up the entries in the routing table in terms of the best match goes to level 1, ultimate route, and so on. So I want you to write step number 1 to 5 and then 6 to 8, all the steps. Okay, just write them down on Microsoft Word as part of the homework questions that I'm asking you to do. All right. Now, what happens if you have a packet that came in and I looked up the routing table and there are 3 entries that can match this 172.16.10 guy? It can match this guy, it will match this, the slash 12, the slash 18, and the slash 26. So who do I send it to? You always send it to the one with the longest match. Remember that. So if a packet comes in and if it matches more than one entry in the routing table, then you send it to the one with the longest match. Okay, and here are IPv6 routing entries. If we have not looked at them yet, remember? Pretty much the same thing. There isn't really no different. Directly connected, the destination IP address, the metric with the administrative distance, right? This is the metric, the hops. This is the exit interface, right? Pretty much the same thing. This is, remember, D means EIGRP, right? So there is really no difference between IPv4 and IPv6. Well, there's a little bit difference in terms of parents. There's hardly any subnetting, so it's a little bit easier to deal with in the routing table. They're all pretty much ultimate routes. Okay, so that ends chapter 7, and hopefully it was enjoyable. Please answer all of these questions that I went over with you, and also don't forget to include the packet tracer. Okay, and until we meet again in chapter 8, God bless.